first example of our discrete Fourier transform. So let's look at this signal in Mathematica and let's start to calculate this out. So let's pull out Mathematica right here. Oh, not right there. Let's get rid of that guy. We've done that before. And let's look at the data set that we're looking. So again, discrete Fourier transforms, we're looking at a discrete data set here. So these are my y values, here. These are my t values in time. And I can just plot these right here. So plotting these values, and you can see the curve looks, let's zoom out for a second. Curve looks very similar to what we see, and exactly similar to what we see in the graph here. So let's go ahead and proceed with our discrete Fourier transforms and specifically our harmonic coefficients. So let's define some values first. So looking at the t data, let's pull that down. So t data, if I take differences, I could see what is that delta t. So let's look at here. So 0.05. So I could just take the mean, or actually I'm just going to take out the first data point. They should all be the same values. So this is my delta t. So delta t is this. I could also look at the length of that data, length of t dat. And here, that's the length of my data. So big N. I can't use N in Mathematica because those are the values. So what else can we determine? Well, my sampling frequency is 1 over my delta t. And actually, I'm going to clear. I did something really bad. In Mathematica, I was just working in a previous notebook, so I need to make sure that I don't do that here. Let's look at it. Let's pull it out and redefine everything, because I saw that delta f pop up in one of my functions. So this is my, again, t dat, delta t, big N, f sub s. So I could, my period is going to be what? This signal is not periodic. It is aperiodic, so it's just going to be n times delta t. I also know what else? Not n. See, this is why you need big N. I also know, so 6 milliseconds, or again, 0.006 seconds. What else can we figure out here? Well, previously we had our expression for our Nyquist frequency as well. So let's go back to this page. So we had a lot of nice definitions. So n, delta t. So let's do Nyquist frequency just to kind of see what our limit is going to be. So f Nyquist is going to be f sub s divided by 2. And we can confirm. So if I do this 1,000, so let's look at, how about I do my f sub s divided by n. I wish I had that big. Anyways, we could see, again, is that equal to my delta f? Ooh, oh, sorry, we haven't defined delta f yet. So delta f is equal to 1 divided by t. And again, that can fs divided by n, same values. Can't stop typing in that. Same values again. That's my delta f in terms of hertz. So that's my function. And if I multiply n divided by 2, so big N divided by 2 times delta f, that should be equal to my Nyquist frequency, which it does. Excellent. Everything's working out in the world. So these are just some definitions. Again, we pulled all these basically just from looking at the t data. I haven't even looked at my the y data just yet. But I'm going to have to look at it in just a second in order to calculate our harmonic coefficients. So let's pull apart and let's develop our code to calculate these harmonic coefficients. So this table, this summing, or this, I gave it away, this summation, we're going to need to use basically a table. And what we're going to do is we're going to pull out, and we need to iterate over R. So what is my, let's look at my DAT. So these are my Y value datas. So I need to pull them out for different R values. So this is an R value of 1. This is my first data point at my first delta t. So I want to pull out Y, or DAT, of, actually let's rename this real quick just to keep it. So I'm going to call this my YR delta t. I'm going to do this my t dat. This. Actually, I'm going to call this. We don't need that. The t dat is fine, but I could get my y delta t. YRT, YR delta. YR delta. So I could pull out now, so my YR delta, I pull out the first data point, that's what we're going to have here, times cosine of 2 times pi times, what's my R value here? 1 times n, which we don't know yet, divided by a big N. That's it. So if I do that, that gives me one value. But I need to do this now. I need to add this. So I need to add the second R value, and this, I'll have to iterate this here. So what I'm going to do is make a table of R, and I'm going to iterate from I goes from 1 to length of YR delta. Oops. I go I get too used to writing I. So that's it. And now I'm going to do, again, this is a summation, so I need to do total. So there it is. So I need to do that. I've done that here. And now I just have to multiply this by 2 over n. 2 divided by big N. So this is my A sub n. There we go. All's, again, hopefully right in the world. And we'll see that in just a second. So let's go ahead and I'm going to also do my B sub n, just like we've done previously. So my B sub n is equal to here. The only thing that changes is going to be our sine function. There we go. I'm going to just suppress this output, but you could double check that in a second. So if I want to calculate my harmonic coefficients, my A sub n, so let's call this my A harm. It's going to be my A sub n slash dot n goes to, let me make a table. And where do I want to integrate this to? Actually, so this is where we're going to show why we have to stop at n over 2, our Nyquist frequency. So I'm going to go from n goes to, slash dot, n goes to I. I'm going to iterate from I goes from 1 to basically the length to big N. Let's just say big N. How about this? So those are my values. Now there's something interesting kind of hidden in here, and we're going to see that kind of pop up in just a second. And actually, how do I calculate my A sub naught? Well, that is just going to be, I know that if n is equal to 0, my cosine is just going to be 1. So actually, let's see if we can do slash dot n goes to 0. We can kind of calculate that value right there. So actually, we can go, let's go from 0 to big N. Again, I don't usually want to do my 0th order harmonics, but let's go ahead and do that here. What about my B harm? Just my B sub n. Now, there's something really interesting about this data set. So this is exactly the reason why we have to stop at our Nyquist frequency. So right now I'm going from 0 to n over 2. So instead, how about I do, if I list plot A harm, what does this look like? Actually, let's do a list. Let's do a list line plot. And let's do plot range all. This function is has mirror symmetry. So around n over 2, so what is our Nyquist? So f, actually, what is the length of our, so our big N is what? 18. So at our point here, and we actually let's do the length of A harm. So 13. So at 7 here, this is our midpoint. So everything across here, there's mirror symmetry. And you can look at this in the data set. Look at last point, first point, last point, same value. Second to last, here. So once you hit that Nyquist frequency, that n over 2, we just have mirror symmetry. So if I just divide this out, so again, once you pass the Nyquist frequency, they're just mirror images of another. These are not real frequencies. We cannot measure anything beyond our Nyquist frequency. We're just getting basically a reflection in your Fourier analysis. So instead, I need to divide this by 2 if I want to look at real frequencies. But again, sometimes you'll see them plot beyond your Nyquist frequency. So you need to be really careful. If you see this mirror symmetry pop up, you know that they plotted this frequency spectrum incorrectly. So let's look at this now. Now this looks a little bit better, or at least, again, there's no mirror symmetry here, so we don't have to worry about if we've gone past our Nyquist frequency. So those are my A sub n's. I know how to calculate my C sub n. C sub n is going to equal to table of square root of A harm I squared plus my B harm I squared. And then I'm going to square root that from I from 1 to length of B harm or A harm, doesn't matter. So those are my C sub n's. How do I plot my F series? It's just going to be series or my F spectrum. is just going to be equal to my table n times delta f from n goes from basically 0 to big N divided by 2. Actually, we don't want to do that. So we want to go in integer values. Actually, this will be fine. So you want to make sure also you're in integer values as well. So go ahead and list plot this. So let's transpose our F series or F spectrum, and then our Cn. That up. And let's see what we've got here. Zoom out to 50. And we have a frequency spectrum. So just like we see in the notes right here. So this, again, from this plot, we could see, again, we're changing it into cyclic frequency just like we've done previously. And all that's changing is your Nyquist frequency. Again, highest frequency is 1,000. What was our Nyquist frequency at the beginning of this? 1,000 hertz right here. So we could see some different behavior, right? Look at the dominant frequency here. This comes at our 0 ortho harmonic, first, second harmonic is our dominant frequency. So again, even though we have the 0 point and we need the 0 point to kind of see this mirror symmetry, make sure that what harmonic you're looking at. So our fundamental frequency here is this 177 or 166.77. So that's your first basically Fourier analysis and Fourier spectrum for discrete Fourier transforms. So next time we're going to look at this concept called we're going to look into this concept of spectral leakage and see that think about it from an engineering perspective. On our frequency spectrum here, we can only see frequencies in intervals of 166.7. What if I have a signal that's 200 hertz? Am I sampling this? Am I getting am I kind of getting any intuition about the magnitude of how that frequency is going to contribute to my signal? No, it's being completely missed. So we're going to look into next time this concept of spectral leakage and how it can be very problematic, especially if we're missing some frequencies on our signal, and how we can resolve that again by our selection of basically f sub s, and actually more importantly for this particular value, our n, so the total number of points. So we'll get into that in the next video. So I'll see you all next time. Thanks. Have a good one.